standard motion is a big deal in calculus. We're going to read through this, and I want you to be very, I want you to pay careful attention to detail, and I really wanted to get a highlighter in your hands, and I forgot, so give me just. So let's read through this top piece here. Particle motion problems deal with particles that are moving along the X or Y axis. Pay attention to that. Come on, there you go. Thus, we are speaking about horizontal or vertical movement. We are just going to be talking in this lesson about horizontal movement. So the particle is going to be moving along a horizontal path along the x-axis. The position, velocity, or acceleration of a particle's motion are defined by functions, but the particle does not move along the graph of the function. I'm going to, well, you're going to see later a velocity graph that looks like that. The particle will not follow this path. The particle is moving left and right on a horizontal path, okay? So please do not assume that the particle is following this motion up and then down and then up. That's not how it works. It moves along an axis. Most of the time we speak of movement along the x-axis. In Unit 6 and 7, particle motion will be revisited, and at that time we'll deal more with vertical motion. For this time, we're going to focus on horizontal motion of particles. I want you to think for just a minute. You throw a ball straight up. So just try to picture you have a ball and you throw it straight up and then it comes down and you catch it. When you throw a ball up, it comes out of your hand and eventually gets to a point where it stops moving, right? It stops going up. Does the speed increase or decrease as the ball goes up? The speed decreases, so it starts out fast and gets slower until it reaches that point where it's not going up anymore at all, and then it comes down. Does the particle gain speed or lose speed as this particle falls? Gain speed. So as we go through these problems, you can kind of refer back to that picture in your head. Also, we will use this sheet about a car and about the gas pedal and your cruise control, mainly the gas pedal, I guess. Let's say you're on cruise control and you want to speed up, you want to accelerate. Acceleration is the second derivative, okay? Acceleration is how your velocity or speed changes. So we're going to deal with position, velocity, and acceleration. Now, let me say this. Sparks will use P of t most of the time to indicate position. Most places will use S of t, and that has something to do with physics. Don't ask me what, I don't know. But the reason that's an S oftentimes for position is something to do with physics and letters that they use. V is for velocity, A is for acceleration, and S is for position. I don't know. All right, average and instantaneous velocity. Now we're going to be using t as our variable. We will not be using x. We're going to use t for time. Suppose P of t, I should have just put these notes online, is a function which defines the position of a moving object at time t. Now I got more to write because I haven't even addressed it, average and instantaneous velocity. Does anybody need more time to get that? Emily, you good? Average velocity is the average rate of the change in position. So that would be P of B minus P of A over B minus A. Like where A is where you started and B is where you ended. No. A is, sorry. A and B would be times. I said that wrong. So the position, where were you at your ending time? Where were you at your starting time? So it's the difference in your position divided by the change in time. Change in position divided by change in time. Like miles per hour, feet per second. Now, that's average. That's like a rock. Instantaneous velocity. This is the last line. Instantaneous velocity is how fast were you going the moment that the tires on your car hit the Illinois River Bridge. P prime of A I'm sorry? Instantaneous. I got too many T's in there, don't I? Instantaneous. There we go. Thank you. Oh, for spelling?
No, it's not.
Instant. Okay. Instantaneous velocity. The velocity at any time A is P prime. You take the derivative of the position.
So is there any similar what we saw last week, A-rock and I-rock? It's kind of the same.
It's very similar. Yeah, absolutely. You're going to need your calculator. Tate. So, a particle's position is given by this function, where P of t is measured in centimeters and t is measured in seconds. Now, one thing you're going to know, if t is measured in seconds, t is not ever going to be negative because t is time. What is the average velocity on the interval 1 to 3 seconds? How do I do that? How do I find the average velocity You're going to have to run that on your calculator because I cannot do e cubed in my head. Yep.
We have a question. So the instantaneous velocity was P of A.
Yep.
But what is the...
Anybody getting any numbers?
For 3,
Okay.
it is 2.8.
Okay. Run the whole thing.
Okay.
Run the whole thing. Because don't round. Hey, do you hear me? Don't round. Use your answer key or do whatever you need to do, but don't round anything until the very last answer. 0.274?
0.274, yeah.
Okay. 0.274 what? What's our unit? Centimeters per second. Remember, that's your average velocity for those first 2 seconds. What's the instantaneous velocity of the particle at time t equals 1.5? So what am I finding? The derivative. I'm trying to find p prime of 1.5, which is v of 1.5. So find the derivative of your position function and evaluate it at 1.5. Now you should get 4.787 for p prime of 1.5. So that's the velocity at that moment in time. What's our unit? Also centimeters per second. You guys having a good visit? Huh? I don't know how much you've learned in science or previous science classes if you're not in physics. Do you know that speed is made up of two components? Do you know what they are? No. I hear what you're saying. No, I hear what you're saying. I hear what you're saying. Velocity has two components, speed and direction. Speed and direction. So I cannot, we'll get to it. I don't want to elaborate there.
Speed and direction.
All right, let's read. Before we proceed, and this is the question you asked. When given a function f of x, how did we find the slope of the secant line from x equal a to x equal b? How did we find the slope of a secant line? So what did we do? F of b minus f of a over b minus a. This is the slope of the secant line. Which also is, now we're going to consider that also to be the what? The average velocity. In terms of position of a particle, to what does the slope of the secant line correspond? We said average velocity. To what does the instantaneous velocity correspond? The derivative, yeah. So f prime of a is the slope of the tangent line, which is instantaneous velocity. I'm spelling it right this time, instantaneous velocity. Anybody need more time? Acceleration. If you are driving and you're not using your cruise and your foot's on your gas pedal and you're staying pretty steady and then you decide you need to pass somebody, what do you do to the gas pedal? So what you are doing is increasing your speed, right? Okay. So acceleration changes your velocity, right? So average and instantaneous acceleration. Average acceleration is the change. Oh, can you write a little line above what I was just going to write? What do I want to say? If P of t is position and P prime of t is the velocity, how would you find your average acceleration? Average, not instantaneous, but average. Divide what by the amount of time?
P prime t.
All right. Remember, if we're trying to find the average velocity, it's the change in position divided by the change in time. To find average acceleration, it's the change in velocity divided by the change in time. So this is going to be V of B minus V of A over B minus A. Your instantaneous acceleration I still don't know why that happens sometimes. Making me work that word again. Instantaneous acceleration. What would the instantaneous acceleration be? We won't divide by anything. Instantaneous is always a derivative, right? So it would be the derivative of the velocity. So it would be here's how I want you to write it. The acceleration at a particular time. Well, that's the same as the derivative of the velocity, which would be the second derivative of position. What's the matter?
Just like you can relate the different graphs, so like whenever it's concave, you could tell what's happening over there.
Indeed.
Is that why we learned all that stuff?
Mm-hmm.
I never learned concave.
You just think through that in your head. Emily. A is acceleration. Mm-hmm. Okay. A particle's position is given by that particular function. That was the same one we were using earlier. What is the average acceleration from 1 to 3 seconds? So how do we find average acceleration? Oh, whoops. Average acceleration is the velocity at time 3 minus the velocity at time 1 divided by 3 times 1. How are you going to let your calculator do that? Have you got the velocity graph? Have you got the velocity graph? Do you have that in your Y2? Yeah, because the first equation you have in your Y1 is this, right?
Yeah.
Which is position. So your Y2, if you have the derivative, that's your velocity, right?
Oh, okay.
So evaluate that velocity function at 3 and 1. Remember, whoop, that's not what I wanted to do.
So wait, this one's the derivative then?
Yeah. See, look, you don't even have to graph it. If you'll do this idea, but where do you have the derivative? Well, you have it in Y2, right? If you'll evaluate the derivative at 3, now mine won't work because I don't have the right equation in there. Minus the derivative at 1, whoops. Make that work? Divided by, now these numbers aren't right because I don't have the right equation in my,
-10.
but this is what you do right here.
Wait, -10. I got -10. Yeah, negative.
Sparks says that it's -10.403.
Yeah.
like that would be like it's slowing down.
Negative acceleration is called deceleration. You are slowing down. You have your cruise on and you take the cruise off. You're going to be slowing down, right? We'll get to your question in just a little bit, or maybe next time, but that's when we're going to talk about this other page, okay? Abby, have you been able to get this number?
Yep, I realized I did the Y1.
Oh, okay. What units would be on this then? Centimeters per second is the velocity, but we're taking the derivative of that, so it's per second per second.
Is that, okay, this is stupid, would that be?
The reason I don't write it as per second squared, you can do it. But at one of my calculus workshops, the teacher said, I don't let my students do that because what's a square second? I said, I don't know what a square second is. He said, this means something. Every second, your acceleration is changing at this many centimeters per second. This doesn't mean jack. So that's why I try to do, ever since then I've tried to do per hour, or per second. Okay, let's look at the next one. What is the instantaneous acceleration of the particle at 1.5? What you going to do?
Double prime.
So how are you going to accomplish the derivative of the derivative on your calculator?
Put it in there. Can we copy that thing and then do Y2?
Absolutely. Absolutely. I don't know how to copy, but this is short.
Oh, sorry.
Is there a copy? I don't know if there is. If there is, I don't know it.
I can't do that.
So now you got position, velocity, acceleration.
Oh, this down.
What, e to the t sine t? And where are we going? 1 to 3? What am I looking for? Oh no. No. That's not what Sparks says.
Oh, wait.
Oh snap. Let's see. Enter.
0.634. Yep.
I hope that's right.
Still the centimeters per second.
Right.
So would we do P double prime of 1.5?
So what you'll write, the instantaneous acceleration. I want you to write this. I know it's come on, Stennett, dummy. V prime of 1.5 equals A of 1.5, which is, what'd you say, 0.634? Centimeters per second. So at that particular moment in time, the velocity is increasing by 0.634 centimeters per second. If we say the velocity is increasing, velocity is in centimeters per second, right? So I can leave off a per second. The velocity is increasing at a rate of 0.634 centimeters per second. Yeah. The velocity is increasing. Am I saying that right?
Because the P is per second.
I would say the acceleration is centimeters per second. But if I'm saying the velocity is changing at a rate, since the acceleration is the first derivative of velocity,
Okay.
since that's just one derivative apart, I'd say centimeters per second. Huh? At that rate. That's a rate. Yeah. It's when I teach this unit that I have big regrets that I have not taken physics classes. Not that you care. All right, here we go. In summary, let's correlate the concepts of position, velocity, and acceleration to what we already know about a function and its second derivative. All right, so here we go. F of x corresponds with, well, hang on, with position. And remember, when we are doing position, velocity, acceleration, we use t for time. We do not use x. F prime of x corresponds with velocity v of t, which is velocity. Oh, let me put something else in here. P prime of t. What does F double prime correspond with? So acceleration, right, which is v prime of t, which is what derivative of the position? The second derivative of the position. And that's acceleration.
On our test, will you pass off for use X?
Will I count off if you use x instead of t? I will consider that a spelling error, okay, which means I will not count off for it.
Sometimes I just accidentally change it.
They will do the same thing.
I get confused with these two.
All right, let's summarize relationships between position, velocity, and acceleration. Do you remember when we did this? If this is f prime of x, then what do we know about f of x? Okay. Now, I will use a little bit different wording, but the idea is the same. What did you know if f prime was 0 or undefined? What did you know about f? Possible relative extrema. That's what you knew, right? So, possible change in direction. Of a moving object. Wait. We'll get to it in this lesson, I promise. We'll get to it. It's left and right. Just wait. Just wait. I promise. We've got some stuff I want to do before we get there. Okay? All right. Now I'm going to erase this because I don't have enough room. Now, we knew if the derivative was 0, what did that tell us about the function itself? If the derivative is positive, we knew increasing, right? So, watch this, because I think this is going to start answering your questions. The position is increasing, which means the particle is moving to the right. Correct. For this one, it's going to be the same thing except the position is decreasing, which means the particle is moving to the left. All we are doing right now is basic position, velocity, and acceleration. So all we are doing is left and right, horizontal movement. You go into engineering, you're going way past horizontal and vertical movement. Three-dimensional. Cal 3, third semester calculus. If you're in engineering, third semester calculus gets into three-dimension stuff. I'll pass on that one. No. Snap. Okay. Now, if the derivative changes from positive to negative, what does that tell you about a function? Which one? If a derivative changes from positive to negative, then the function changed from increasing to decreasing, right? So, what do you think this tells us? The particle changes from moving right to moving left, yeah.
So, up is right,
Increasing is right, decreasing is left.
what if it's like on, if it's derivative though, if it's just like that,
Just wait. Please, I promise it'll come. It'll come. Is this answering some of the questions you had at the beginning? Now, what if your derivative changes from negative to positive? Your particle will change from moving left to moving right. Are we out at 2 o'clock straight up? Let's do the acceleration table at the bottom and we'll call it a week, okay? All right. What derivative is acceleration? Yep. What derivative is velocity? Now, sometimes I just have to go over here and think about the original function. Let's not think acceleration and velocity. Let's think f double prime, f prime, f. If f double prime is 0 or undefined, what did that tell me about the function itself? Potential. We knew that there was a possible POI, right? Now, if there's a possible point of inflection, what did that tell us about the derivative? Changed from increasing to decreasing or the other way, right? So let's talk about what it means here. This is a potential change in sign of your velocity, meaning positive velocity moving right versus negative velocity moving left. What if the second derivative is positive, what does that tell us about the derivative? Increasing. So if the acceleration is positive, then your velocity is increasing. If the second derivative is positive, then your function is concave up. That's correct. If your second derivative is negative, f prime is decreasing, which means your velocity is decreasing. What if your second derivative, your acceleration, changes from positive to negative? What does that do for your velocity? Changes from increasing to decreasing. And then you should know the last one. If your acceleration changes from negative to positive, your velocity will be changing from decreasing to increasing, according.